Steve Millidge. I am the founder of Payara, and this webinar is supercharging JavaEE applications using JCache with Payara and Hazelcast. What we're going to do is go through a little story and demonstrate using Payara in a very typical REST API to essentially speed up applications. So what we're going to talk about is a scenario that we all know and love. So essentially around pizza. So imagine that you work for a pizza delivery company, building web applications, and marketing have a fantastic idea. So they imagine that you need a new mobile web application so that your customers can order pizza from their phone wherever they are and track orders, track the delivery, all those wonderful things that you'd want to do while eating pizza or ordering pizza. And you as the poor web developer or mobile developer are basically assigned to build this application. Luckily for you, or unlucky for you, essentially someone has already built you a pizza store connector, which is a third-party API to a pizza store backend, which is a third-party application. And the architecture that you've been asked to build essentially is to build a cloud solution running in JavaEE as the backend to the mobile interface. This will talk to this third-party pizza store connector API, which unfortunately for you is using the sort of wet string protocol to talk to the pizza store backend. So it's not the fastest thing in the world. And you as a developer have been tasked to make this support 50,000 users on the lowest price, the lowest lowest tech possible. So what we're going to do is we're going to have a quick look at the pizza connector code that you've been given, just so to check it out what the interface looks like. So here's the interface to the pizza store connector. Essentially, it's got a bunch of standard sort of APIs. We have find customer by ID, which takes an ID. We've got APIs to get an order based on identifier. We have a lovely API here which essentially gets all the order IDs for a specific identifier. And various other sort of APIs like place order, cancel order, create customer, sort of standard sort of CRUD API on some connector that you've been given. If we look at the actual code of this, just make it a little bit bigger. So obviously I have dummied out something here, but the code is pretty horrible. So if we take the get orders for customer API, we essentially get a customer ID. It uses another API to find it. It then uses another API to get the order identifiers in longs, and then it loops through every single one, making a remote API call, if you remember our architecture. And then it returns these objects. Unfortunately, each one of these APIs that you have to call within that method have a huge chunk of latency in there. So this is not going to be fast. The API has a lot of latency, and it's not going to be quick. And for example, if our API that we built, so our application that we build on top of this, is a standard RESTful application. So I'll just open up a REST web service to get the customer orders. So this is the API that we built for our mobile application. So essentially it's going to be a standard Java JAX-RS RESTful service. So we have the path for customers, it's a customer order resource that uses our pizza connector, and then it will use CDI to inject the connector and essentially just call the connector and write out the answer as JSON. So very typical simple build of a REST API onto a backend data source of very high latency. So if we actually run this API, I'm going to run this in embedded Payara, which I'll come to later. But if we essentially run this REST service and test it out, we'll see that it is pretty slow. So once that's booted up, okay, and we'll switch to the browser and just find the customer orders for customer 1. You can see it takes quite a while to run, deliberately, obviously. So this is representing a low latency service. And there we go. It took a long time to run because each one of the method calls that it has to do, which are remote, and each one is low latency. So we can see we have our JSON representing the orders for Sherlock Holmes, who lives at 221B Baker Street in Marylebone in London. So that's the task that you've been given by your management. You need to create this mobile interface. It needs to use that connector, which is pretty poorly designed, pretty poor latency, and you need to support 50,000 users. So the problems that we have with our connector, obviously, is it's high latency, has multiple API round trips over effectively some wet strings, seems to be what they built it on. The data model involves lots of remote calls, not ideal, not what you want. And you know fine well that this is just never going to scale to the volumes that you've been told to build this to. And it's too costly to rewrite. So we all should probably recognize this problem. We've all seen this when accessing legacy systems, legacy databases. And we face this day to day in many application development problems. So the question is, what do we do now? How do we speed this up? And obviously the answer that we're talking about today is using JCache, which is a Java temporary caching API, or JSL 107. So let's look at how we could rapidly speed this up. So if we go to the code for our web service, so our RESTful service. So let's take a look at that. So again, this is the RESTful service we just invoked, and we can see that it uses the connector to do get orders for customer. So let's go to our connector again, and here's the get orders for customer. So what we're going to do here to speed this up is we're going to put in caching using Hazelcast and Payara, again, which we'll come to a little bit later, and using CDI level annotation that's provided by the JCache API. And we're going to call it, it's called @cacheResult. So if we add that annotation, which is a Java API annotation. I'm actually doing it on the wrong class, so bear with me. So if we do it here, problem with live coding. So if we find the get orders for customer, which uses the connector, the remote connector, and we add onto their cache result, which again, let's say is a Java JSR 107 API. Then if we now rebuild that web application, just stop my embedded server and rebuild our web application. What the cache result API does is it, as it says on the tin, it caches the result of the call, which we'll see. So we'll just build this through Maven. And then once that's built, we will run our embedded Payara application server. And then try it again. So you can see Payara embeds Hazelcast, and it's during this boot here, you can see that Hazelcast 3.4 has been booted up, and it's formed a cluster of essentially one server, as we're just running one at the moment. It seems to be running very slowly, and we have our server running. So let's test the application again. So we'll see the first time we hit, it takes a long time, as it did before, basically to go off to this pizza connector to the pizza store backend and find our orders. However, the second time now we run it, it's fast. There we go. So you can run that many times. And now the API is fast, and we essentially removed the latency between our RESTful web service and our pizza store backend. In addition to that, we can also run a couple more of these embedded Payaras to essentially give us a cluster of REST services. So we just go to our code to route running the embedded Payara. Let's make that bigger. So this is the code that we're using to run the RESTful service we're creating. So this is using Payara. Payara is a variant of GlassFish, and we're using an embedded Payara here to run it straight from a JVM, rather than booting up an application server, deploying through the console, etc. And this is all the code really needed to do to boot Payara did within a JVM and running GlassFish. So if we walk through this, essentially we have a set of properties. The one I'm going to have to change, which is the listen address if I want to run a second one. We then create a new GlassFish from those properties, start it up, and then run what's called an ASAdmin command, which is a command line command for configuring the GlassFish embedded server. And what we're doing in that is we're actually essentially enabling Hazelcast. So we're setting Hazelcast configuration enabled to true. And then on this line, we're actually deploying the WAR file that we just built. So if I run this again, so this will give us a second copy of the RESTful service. So we've got the second one booting up here. What you'll see is, if I make it a bit bigger, is this is the second REST service booting, and they will form a cluster. So there you see that we have member 1 and member 2, and we now have two REST services that have formed a Hazelcast cluster, which is basically a distributed cache. And the reason I'm showing you that is, you can see on the second one, is that again we have two nodes in the first one. The first server we ran can see 2 nodes, and the second server can also see 2 Hazelcast nodes. So we have a clustered service. And the benefit of that is we just started this second server on port 8081. So if we change the port on our browser to 8081 and run the same service again that we had before, essentially that service comes back quick. And that's because the cache that we have in Hazelcast is shared between all the different REST services. So if you wanted to boot up multiple REST microservices for this RESTful service on multiple machines and load balance them, they would all share the same cache. So again, the second service is already fast. So let's go back to what we did to that pizza store connector bean, and just to recap. You can see that all we've done to speed this service up is to add cache result. So let's just go back to the presentation. So essentially, as a developer, be as all round. You've added 12 characters to your application, and now magically it can scale and latency's disappeared, and we can support many, many thousands of requests a second across multiple RESTful microservices. Fantastic. Time to go home. So what just happened? What magic have we just done that 12 characters has magically speeded up our application? So let's look a bit under the covers to see what just happened there. So JSR 107, which is the API that cache result CDI annotation comes from, essentially has these core concepts. We have a caching provider, which is a product level class, which in this case is Hazelcast. That is our provider of caching capabilities to the JVM. And in the case of Payara, that's embedded and shipped with the latest release of Payara. The caching provider gives you many cache managers. Cache managers have a cache, and that cache contains many entries which are key value pairs. So essentially we have a distributed hash map storing our data, or potentially many distributed hash maps. So essentially the caching provider retrieves and closes cache managers, the cache manager creates and destroys, and the cache contains your objects, in which case, if we quickly zoom back to our code, in this case the objects will be this customer. That's the object that will be placed into the cache. But in that code, that's those 12 characters, we don't see any of this. And this is the magic, essentially, of the CDI API. So what is happening behind the covers, and this is the CDI implementation is provided by Payara. It's the standard CDI interceptor. And what it does within the code, as soon as you add that cache result, during the interception, it essentially obtains a cache manager from the caching provider. It basically creates a cache based on the name of the method. So the cache that it will create will be public get orders for customer. It'll actually have the fully qualified cache name, brackets, long. That'll be the name of the cache, but you don't really need to know that. That's opaque to you if you don't use parameters to the annotation. It will then look at that cache in the cache manager. If it's not there, it will create the cache for you. It will then take your method parameter values and create a key. So it will take long customer ID and make that a key. If you have multiple method parameters, it will take each parameter and concatenate them into a special class and create a key from the combined parameters. Creates that cache key. It does a cache get before it invokes your method. If that cache get returns an object that has been previously stored at that key, it just returns that object and it doesn't invoke your method. And so in our case, if there's already an object with customer ID 1, then it doesn't invoke that piece of code, which essentially, as that piece of code then goes off to the backend store through the latent API, it is never invoked. And if it's not in the cache, it does invoke your method, takes return value, and then puts that object in the cache for you. So essentially, if we put all that into rough JSR 107 or JCache standard API calls, it essentially does all this set of calls, slightly a bit more logic, but for you. So gets the caching provider, gets the cache manager, creates a configuration, sets up the configuration, creates a cache with the method, which would be the method name, etc. Creates a key for you, and then puts the result of your method call into that cache. All magic. So let's look a little bit at what other CDI APIs we have. So as well as cache result, which essentially caches the result of a method call, we have cache put, which basically will cache a specific method parameter. We'll see a little bit, we'll try play a little bit with that in the code in a minute. There's also cache remove, and that removes a cache entry based on the parameters. And there's cache remove all, which obviously takes all entries from the cache. And the cache name itself can actually be configured on the annotation. So if you open this up, you can actually see that there's a bunch of parameters, which may be a little bit small to see on this screen, but one of them is cache name. So we could actually, rather than having a name created for us, which in this case would be some mangling of the method name, we could just create it to a customer order cache or something like that. There are various other parameters on cache result annotation. Some of them are more complicated, like cache key generator, so you can use a generated key that isn't the one that's provided by the API internally. So Payara provides a cache key generator which concatenates all the method parameters and generates a key from them. But another one is cached exceptions, is if an exception is thrown, whether that should be cached, so that the next time the method is invoked, the same exception will be thrown back again without actually invoking your method. Which is slightly strange, but you can do that. And there's non-cached exceptions as well, which will basically, if that exception is thrown, it won't cache that exception in the cache. Let's have a quick look. So, just a little bit about Payara. Payara is a version of GlassFish server. So we take open source GlassFish server. We provide support for it. We provide development for it, and we create enhancements like this Hazelcast JCache implementation. And Payara is a drop-in replacement for GlassFish. We do quarterly releases. We provide enhancements, bug fixes, patches, all those sort of things. And our latest release embeds Hazelcast for session persistence and JSR 107 API support. So if we look a little bit further into the code, just to show a little bit more API, what we do is, what would we want to do if we wanted to build this API out and add further caching into it? So let's use some of the other annotations that are available to us. So this one here is obviously pretty simple. That would be, again, a cache result, because what would you want to do in this case? So if we're manipulating our cache, if we've got a identifier and we're returning the customer, then the best thing to do would be to store that customer into the cache so that we don't have to go to the backend service again. So we would put it in a cache called, say, for example, customer. Similar for this one. This is a simple, get a read API. So let's, again, that one would have cache result. But that would probably go into an orders cache. So let's call it the order cache. Orders. Let's call that customers cache and orders cache. Place order is different though. Place order is we're creating a new order object here, and we have it's for a specific customer, and it's going in the order, and we have an order identifier. In this case, what we'd want to do typically would be then to place this into the orders cache. So when we do get order by ID, we can return it direct from the cache, and that's where essentially cache put comes from. So what we do here is cache name and make that the same cache as here. So import. So that would, what this would do, we need to also add in another annotation on the method parameters. So we need cache key. Just disappeared. Add the import for that. And cache value. So what those annotations do, you need to put the cache name, otherwise the name it would use by default, as I said earlier, would be some mangling of the method name, which means that if we left it blank and didn't put the same name here, these two would be placing and retrieving data from different caches. So adding the cache name the same means the cache put will put objects into the same cache as a cache result. And what this does is these two parameters here, this says this is the key that we're going to use, which is the order ID identifier, order ID, which is the same key as we're using here. And that says the cache value says that's the value. So what this method will do is, with these annotations now, when it executes, it will take the order and put it into the orders cache with the key order ID, and then it will invoke the place order method, which is what you wanted to do. Similar for cancel, we would want to do cache remove, and what that would do is, as soon as that came, this class is invoked with that order ID, it would remove the entry from the, just add the cache name, it would remove the entry from the orders cache with the key order identifier, order ID. And similar for create customer, that would be a cache put. Into the customer's cache, and that would be the cache key, and that would be the cache value. So that would give us a essentially a CDI bean that's using our pizza store connector that we've been given by our third party, and actually build caching around that, so that we're manipulating the cache, the shared cache across the multiple RESTful web services, depending on whether we're creating, updating, or deleting objects within that cache. So if we want to do an update, we would then use a cache put as well. So if we did an update method, we'd want it to use cache put. So using the CDI annotations is a very, very simple way of adding caching, distributed caching to your applications. And what you saw from the two RESTful services, it also adds a sort of clustered, highly available cache to your RESTful web services. That's essentially provided by Hazelcast. So if we go back to the slides. So what Payara does is Payara essentially embeds Hazelcast, and it embeds it in a number of ways. So Hazelcast is embedded for session persistence. So from within Payara, you can set your web sessions to be stored within a Hazelcast cluster. That means they are automatically stored in a highly resilient, highly distributed data store, very scalable. It also embeds the JSR 107 APIs that we've been demonstrating. So that allows you to use both the JSR 107 APIs, both annotations, CDI annotations, and the actual JSR APIs like Cache Manager, caching provider, cache, etc., which we haven't demonstrated in this webinar for time. And it also actually gives you access to the raw Hazelcast API. So Hazelcast itself has way more capabilities than provided through the JSR 107 API, which is a bit of a lowest common denominator API. So Hazelcast has much more powerful capabilities, and through Payara you can actually just look up a Hazelcast instance through JNDI, or you can inject one through CDI and use the Hazelcast APIs directly. And Payara itself also provides all the CDI annotations. So the CDI annotations that you see within this code here have to be provided by your container. They're not provided by the Hazelcast. They're provided by obviously your application server containers, as they need to integrate with the application server itself to find the caches, look at the caching provider, etc. So they are provided, and it must be provided by your application server. So within Payara, these are provided directly by Payara itself. So there's nothing in our web.xml. If I just show you quickly, if I can find it, in our beans.xml, it's not there. So we're not having to add the annotations, sorry, the interceptors to our beans.xml. They're all done. So there's our beans.xml. They're all done by Payara itself. So just to summarize, done that bit. So actually using JCache with Hazelcast on Payara is incredibly simple. As we saw, 12 characters is enough for you to start caching data within Hazelcast on a highly distributed, resilient caching infrastructure, and speed up any latency that you may have with some back-end APIs or wherever. It's built into Payara, and using Payara embedded, we saw that it's only a few lines to actually build a microservice, a RESTful microservice in Payara embedded, which you can just start on from the normal Java command line with a normal main, and that can also use Hazelcast completely. And Hazelcast itself gives Payara performance, resilience, and scalability to these caches. So it does that through both web session persistence, and then for your own applications, you can get that resilience and performance. So that's all I've got to say at the moment. So if there's any questions, start taking questions. Okay, so we've got one question. Is the demo project available on GitHub? Not at this moment in time, but it probably will be by the end of today. I can get that up there pretty easy. I'll put it on Payara GitHub. I can't remember if there was a... Yeah, there is a final slide. which shows you where get more information around Payara. So we can get Payara's on GitHub, all the source and Payara development's done on GitHub, and I'll place the code up on there as well. Okay, so what other app servers can be used? That is an interesting question. So in the sense of CDI, like I said in the last couple of slides, so CDI integration needs to be provided by the application server. Alternatively, you can get a CDI interceptor implementation and add it into your beans.xml. There is a reference implementation, which we haven't tested. We built our own. So that would have to go to use JSR 107 with another application server. I'm not aware of any that build in JSR 107 at the moment. You can build an application where you package up Hazelcast added on the system class path, or you could package it up in your WAR, use the JSR 107 APIs to get at the Hazelcast cluster and to boot it up, and you could then use a CDI annotation, sorry, a CDI jar, add the interceptors into your beans.xml, and that would give you the full CDI annotations as well as the JSR 107 raw API. So it's possible to do it on other application servers. In Payara, it's all built in, so you don't need to deploy or do anything like that. I'm sure that later application servers will start bundling in a JSR 107 implementation. I know it's possible on WebLogic to use coherence. I'm not so sure on others. So we have a question which is, I assume the answer is no, but based on the nature of implementation and context, but for the sake of asking, if someone decides to use Spring for the cache layer and Payara and Hazelcast, it's just fine, right? And that is the question. So I haven't tested it. You can deploy Spring on Payara. It's a full JavaEE, well, because it uses GlassFish on, as its internals. It's a fully JavaEE 7 compliant. We did fix some bugs around Spring to get some of the Spring guys raised, so definitely it works with Spring. I don't know about Hazelcast integration with Spring. I know Spring has its own caching API. I suspect there will be a Hazelcast implementation for that, but I don't know. So I imagine if you bundle all that together, it would work fine on Payara. Okay, so about Hazelcast, another question about Hazelcast and Payara. Where do we keep the hz config file? Okay, that's a good question. So within Payara itself, I haven't got it running here. There is a setting that you can use to tell it where the Hazelcast config file is. So if we go in here, I haven't got a Payara running. I could get one running, but it'll take a little while. If I go to the embedded code, there is this set Hazelcast configuration function. Sorry, command line command. This command, sorry, that you run has actually got other parameters. One of which is to tell it where the Hazelcast configuration file is. That's all documented on our wiki on the GitHub. And within if you run the full Payara, not the embedded, and it has the admin console installed, there is a tab on the admin console called Hazelcast, which will tell you where you can give it the path to the Hazelcast config file. Okay, so another question related to that, which is in Payara, where did you configure Hazelcast as a cache provider? Okay, we don't actually need to within Payara because it's built in. So this actually command here essentially basically bootstraps the embedded Hazelcast caching provider. So that is all in there. If you wanted to use a different one, then you'd likely have to use the JSL 107 API directly and give it the correct URI when you choose what your caching provider is, if you have a different one packaged in with your application in your WAR file. Otherwise, it's Hazelcast currently embedded with a default configuration. And the actually retrieving the caching provider is actually done within our CDI annotations. Payara also comes with, it basically takes a caching provider and pushes it into JNDI, and we also have CDI annotations to inject the caching provider, which I haven't shown in this, but it's all in our wiki. You can. So another question is, can you use the rest of the JCache API? Yep, absolutely, no problem. You can use the rest of the JCache API directly. There is a way to inject the caching provider within Payara. So we can, probably won't compile, but I'll show you there is you can essentially just do, that's actually a way to inject the cache manager as well. So you can actually just do that inject in Payara. This will only work in Payara because it's not JSL 107. You can actually just do an inject cache manager like that. Whether it works at the moment on this project is another matter, but that's how you would use it in Payara. That is not JSL 107. That is just an extension in Payara that allows you to get hold of the cache manager. You would still be able to use caching, get provider, get cache manager if you needed to. The one thing to watch is if you're using, this will apply to almost all implementations. If you're using CDI and JSL 107 API together in the same application, which you can, is the keys that are generated will not just be the long. They will, if we look in here again, there is a class that you can give it, which is the cache key generator class. That is provided by the CDI implementation, and that will generate typically a CDI implementation specific key class, which in our case is a Payara generated key. So that they will be your keys if you need to use the, if you wanted to interoperate between, for example, JCache code, direct API code to talk to retrieve objects from the customer order cache, the key that you would use would be one of these Payara generated key objects, which would take a customer ID. So typically it's not typical to interact both for CDI and direct with the API on the same cache, but it is possible. It's non-standard. Okay, the question is, you mentioned using Hazelcast in embedded mode. Any downside from the prior side if we go with a smart client? To be honest, we haven't tested it, but we don't see why it wouldn't work, because it would be a config setting. But I can't see any downside. In fact, there is upsides in the sense that you can move your cache tier out of the JVM of the application server, which would give you potentially better options for tuning. So you can tune your cache JVMs for large static populations and large heap sizes, and maybe your application server JVMs for throughput and rapid turnover, rapid garbage collection. So there are benefits of moving into a client server architecture where your objects are cached in remotely. The thing you'd have to watch is if you have them in remote Hazelcast nodes that aren't Payara application servers, then you will have to make sure that your classes that you need to cache are on the class path of those Hazelcast remote nodes. So in that case, you need to take your var. If you're going to cache classes that are defined in the var, you need to make sure that they are on the class path of those remote JVMs. So they won't be effectively deployed to them. You need to set them up on the class path directly. Okay, that's all the questions. I'll pass it back over to Andrea.
Okay, thanks so much, Steve, and thank you everyone for attending. We've recorded this webinar and we'll be posting it on hazelcast.com as well as the slides and the link to GitHub directly. Thanks again.